Today, we're turning our eyes upward, way, way upward, to look at a cosmic event of literally unimaginable scale that's constantly hurtling our way. We're going to track the journey of a colossal natural phenomenon straight from the surface of our star directly into the fragile, hyper-connected systems that keep our modern world running.
Okay, let's dive into this with a number that's really going to set the stage for everything we talk about today. 1 billion. And hey, we aren't talking about dollars or data points here. We're talking about weight. The sun regularly ejects 1 billion tons of charged, magnetized plasma out into the solar system in just a single, violent outburst. It's a mass of just unimaginable size, tearing loose right from the sun's corona.
So, this leads us to the ultimate question we need to answer today. What exactly happens when the sun throws 1 billion tons of itself directly at Earth? Our planet, as you know, is covered in highly sensitive, hyper-connected electrical infrastructure. When this incredible mass of solar material targets our fragile blue dot, it sparks a chain of events that has the potential to change our entire way of life in an absolute instant. Section 1, the billion-ton sunburst, anatomy of a solar eruption.
We know this as a coronal mass ejection, or a CME for short. The corona is basically a haze of ionized gas trapped by magnetic field lines looping right out of the sun's surface. But when those loops snap, the plasma inside is flung outward as a self-contained bubble of charged particles and magnetic fields. And remember, when space forecasters say billions of tons, that isn't some dramatic metaphor. It is a literal, terrifying measurement of what's heading out into space.
To really ground that staggering scale in reality for a second, a typical CME contains somewhere between 1 billion and 10 billion tons of material. That's a mass roughly equal to about 3,000 fully loaded oil supertankers. Now imagine all 3,000 of those supertankers just moving through space at a few percent of the speed of light. We're talking speeds that can easily top 3 million kilometers per hour. That's the sheer physical force we're dealing with here. It's basically the worst traffic hazard in the entire universe.
Section 2, racing across the solar system, the 150 million kilometer sprint. And this brilliantly illustrates a critical challenge in space weather forecasting, the massive difference between seeing the storm and actually feeling it. NASA classifies solar flares and CMEs as the absolutely most energetic phenomena the sun produces. The flare, well, that's just the flash of light. That light reaches Earth in about 8 minutes and 20 seconds, giving us our very first warning. But the mass, the CME itself, is a lot slower. A slow one may take 3 or 4 days. But a fast one? A fast one can cross that entire 150 million kilometer gap in well under 24 hours. The absolute fastest take just 14 to 18 hours. It's enough time to see it coming, sure, but nowhere near enough time to safely disconnect a massive continental power grid. And the thing is, these CMEs aren't aimed. They just erupt wherever the magnetic loop happens to be pointing at the time. Most of them actually miss Earth entirely, but their reach is just astounding. Earlier this year, the sun launched a CME directly at 3I/Atlas, which is an interstellar comet passing through our inner solar system. This billion-ton plasma cloud literally chased down an interstellar object across 200 million kilometers just to strike it. It's a hugely humbling reminder of the sheer energy involved when the sun decides to take a shot. Section 3, when plasma hits the grid, from the sky directly into your power lines. So let's look at how this actually builds into a mechanical failure here on the ground. The plasma doesn't actually touch the surface. Our planet's magnetic field thankfully deflects most of it. But as it slams into our shield, it creates a massive disturbance. This rapidly changing magnetic field essentially turns every high-voltage transmission line and undersea cable into a giant, continent-sized antenna, soaking up massive geomagnetically induced currents, or GICs. These slow-varying currents push right into transformers that were just never built to handle them, completely saturating their iron cores. Ultimately, the transformers wildly overheat, and in the absolute worst cases, the metal windings physically melt down. Section 4. History's warning signs. Proof that the threat is not theoretical. You know, back in 1859, the Carrington event, which remains one of the most powerful CMEs on record, hit when our most advanced tech was literally just the telegraph. Equipment sparked and ran without batteries, functioning purely on current pulled right from the sky. Fast forward to 1989, a moderate CME collapsed the entire Quebec power grid in a matter of minutes, leaving millions completely in the dark. Environmental historians actually view 1989 as just a mild preview of what's possible. Then jump to May 2024, and we experienced a massive G5 aurora storm. And right now, we're sitting right in the peak of solar cycle 25, which is running far hotter and more active than anyone originally predicted.
Now, what's really interesting about this phenomenon is how those severe G5 events are actually born. See, the sun can launch multiple flares in really rapid succession. When a faster CME catches up to a slower one that's already in flight, they merge into what forecasters call a cannibal CME. It essentially becomes this monstrous compound storm that hits Earth much harder than either component would on its own. That spectacular May 2024 storm we just talked about, that was exactly this kind of compound event.
Section 5. The fragile modern world, a civilization wired into the atmosphere. Consider the number 10,000 for a second. That is the number of active satellites currently sitting right now in low Earth orbit. Above the atmosphere, the effect of a CME is entirely direct. These 10,000 satellites are sitting directly in the crosshairs. Their electronics get bombarded, solar panels degrade, and as the storm heats up and expands our upper atmosphere, it creates physical drag that can literally pull newly launched satellites right down out of orbit. We saw this recently when the Chandrayaan-2 orbiter measured a solar superstorm inflating the moon's thin atmosphere 384,000 kilometers away. The reach is just phenomenal, and literally everything above our heads is entirely exposed. But the danger below the atmosphere down here, with us, it's even more dire. So the crucial point is this. The real horror of a Carrington-class event isn't just a rapid, temporary blackout. It's the years of restoration. Extra high-voltage transformers weigh several hundred tons each. Very few countries actually manufacture them, and they absolutely cannot be stockpiled at scale. If a storm burns out even a few hundred of these simultaneously across an entire continent, you're looking at a replacement queue of over a year, maybe even 2. And think about it. A wait time of 12 to 24 months for power triggers an unbelievable cascading logistical nightmare. Without those transformers, you have a long-term loss of refrigeration for food and medicine, water treatment facilities halt, fuel distribution stops entirely. On top of all that, a severe storm disrupts the ionosphere, degrading the GPS timing signals that global banking, telecommunications, and aviation rely on just to synchronize. Even our submarine cables, the ones carrying the world's internet traffic, become massive antennas, soaking up those destructive currents. So you wouldn't even be able to doom scroll while the fridge thaws out. Which brings us right back to the present moment. The sun is loaded. Solar cycle 25 has completely exceeded early projections, and X-class flares have basically become routine at this point. The solar maximum is expected to persist through late 2026 and well into 2027. During this window, the sun is going to routinely take shots, launching billion-ton plasma clouds into the solar system. Now, most will miss us, some might just graze us, but the statistical reality is that eventually one will not. The gap between Earth and the sun is undeniably vast, but whatever the sun launches today can literally be here before tomorrow's evening news. We've built an incredibly advanced, beautifully interconnected world, but one that is inherently fragile to the ancient, inevitable weather of our cosmos. So I'll leave you with this final thought to consider. The sun will keep launching these billion-ton plasma clouds. What happens to our fragile, heavily wired world when one finally doesn't miss?